we defined a formal ring, the Grothendieck ring of basic semi-algebraic formulas, and we also define a morphism, capital pi, from this ring to the Grothendieck ring of algebraic or quasi-projective algebraic varieties tensored by polynomial with coefficients, integers, and variable 1 over 2, given by an inductive process. And the idea was the following: to define pi of a formula with a given inequality. We take the mean value of 2 points of view. The first one consists in adding a variable here, a new variable y, with a square. So we have a double cover out of the set of points where R is 0. In my picture, R is simply the stupid polynomial x. So I divide here by 2 because I have 2 points. Here I have the locus of points where R is 0. So as you see, for these special points here, I only have the point divided by 2, which is too much, so I have to subtract here the point, but the point is the locus where R is 0. So this is the first point of view, and the second one is the point of view, the complement point of view. Here I consider the double cover given by y square plus R. Okay. Same game, I have 2 points here. So I have to divide by 2 in order to get the half line. Okay. But here I have also a special point here. I don't want this special point to be in my set here, my set of points satisfying this formula. So I have to add this point in red now to the red covering. Okay, so I have to add half of the branch locus in taking the complement. So here I take the complement in the space of in the total space. So minus y square plus the branch locus. Okay. Parentheses. So it gives 1 over 4 a y square equal R minus a y square equal minus R. So here, this and this. Okay. And I have here 1/2 the class of the total space minus minus what? Minus 2 times this guy. So yeah. Okay. Oops. Here I have 1/2 here. Okay. I don't divide by 2 the total space. So I have. But I have 2 times this guy. And I have a 1/2 in front of this term. But by additivity, this is nothing else than A are different from 0. So the realization is given by the following inductive formula: 1/4 A y square R minus A y square minus R plus 1/2 A and that's it. So you see that starting from this formula with n+1 inequalities, we get a combination with coefficients in this ring of formulas with n equalities, and so on. And the proposition was that this realization is a morphism of ring. This is a morphism of ring, and the restriction to pi, restriction of pi to the set of to the subring of subring given by the inclusion in this ring of the Grothendieck ring of algebraic varieties. So this restriction is the identity restricted to this ring. Okay. So we do nothing through this realization. We do nothing for classes of algebraic varieties. You can see this in the inductive process. If there is no equality, there is nothing to do. So let us compute a very easy example. We try to understand the realization of this class. So the set of points satisfying this formula is the open half line. So we apply the inductive formula only once, because we only have one inequality. And we have to consider here y square equal x minus y square equal minus x plus 1/2 x different from 0. So here I have the class of an algebraic varieties, which is a parabola, and Okay. So this is nothing else than the class of the line. This is L. Okay. But for the same reason, here for this class, I have the other parabola, and of course, for the same reason, in the Grothendieck ring of algebraic varieties, this is a class of R because we have an algebraic isomorphism from the line to the parabola given by the projection. So yes, and here what I have is the real line minus a point in the Grothendieck ring of algebraic variety. So by additivity, I have L minus 1. Yes. So it gives 1 over 2 L minus 1. And now using products. Using product, you can compute the class of the half plane in R2. Now you have to see this polynomial as a polynomial in two variables, x1, x2, and this formula gives this half plane. But the half plane is a product of a line by the semi-line. So by the product formula, we have okay. This is the way we compute. So it seems that in this ring we obtain polynomials in L, but this is not true. For stupid example, we are able to compute the class of algebraic varieties using the class of the line, but this is not a real life. Okay. Usually we have classes of algebraic varieties, and we cannot obtain those algebraic varieties as polynomials in the class of the line. Okay. No hope for this. So what I'm saying is that we accept some stupid examples, we are not able to compute in this ring. You may write a formal combination of algebraic varieties, but at some point we have to stop because we cannot express those classes of algebraic varieties as a simple, more simple classes. Okay, the point, the interesting point in our ring is the following. The computation we make, even through the realization pi, in fact, really says something about the complexity of the formulas we start with. It has almost nothing to do with a set of points satisfying the formulas. It has to do with the complexity, the algebraic, the logical complexity of the formulas. For instance, let us consider this formula. Everyone agrees with the fact that there is no point satisfying this formula in the real case. Okay? But nevertheless, so you have to understand this formula as the complement of the formula with the relation in the opposite direction. Okay? Nevertheless, a quite easy computation gives 1 over 4 L plus 1, which is not 0 in the Grothendieck ring. Okay. So a set of points satisfying a given formula may be empty, but even through the realization, what we obtain is maybe not 0. And much more than this, for instance, in our paper, we give this example for polynomial p. Showing this. Okay, so now let's try to give even more simple realization than the realization pi. We have this injection. And we have this realization. So using this realization, you see that a class of a basic semi-algebraic formula may be seen as a linear combination of class of algebraic varieties. So since we have a combination of classes of real algebraic varieties, we may take here the virtual Poincaré polynomial on those classes. We may apply to each class the virtual Poincaré polynomial to the set of points given by the equation that gives the algebraic variety. Here we have, but of course, beta apply on this factor. So beta has to go through 1/2 powers of 1/2 coefficients. Okay? So you get you finally get a polynomial with coefficients in this ring. And since we do nothing through pi for classes of algebraic varieties, we have this diagram. Now here we have a polynomial. The proposition is that this realization is a morphism again. And we can take lower realization again by evaluating this polynomial at -1. If we do that, it seems that we obtain some combinations of powers of 1/2, combination with integers coefficient. Okay. But in fact, taking this realization, we fall in the set of in the integers, and we do nothing else than taking the Euler characteristic of the set of points satisfying the formula. So going this way, pi, beta, and evaluating at -1 is the same as taking the set of points, the semi-algebraic set of points satisfying this formula, and compute the Euler characteristic of this set of points. So for instance, here, if I take this formula, and if I apply now beta, I found u plus 1. And if I evaluate at minus 1, I found 0. But the set of points satisfying, the semi-algebraic set of points satisfying this formula is the empty set. So this is what I said here in generality. We found the Euler characteristic of the set of points satisfying this formula. Same thing here. Okay. And Sébastien, you look at this formula to check my proposition. If you take beta, you get 1 over 2 u minus 1. And now if you evaluate at minus 1, you find minus 1. And minus 1 is the Euler characteristic of the line or the half line. It's the same. Okay. So you may find, at this level, you may find non-zero polynomials for basic semi-algebraic formulas with empty set of points. This is possible. But if you take the lowest realization possible evaluating at minus 1, of course you find 0. And this is the end of lecture 3. So now lecture 4. Maybe it's better to say motivique. Yeah. Milnor fiber. I start with the complex situation already described by Michel. I take a germ of a polynomial germ from Cn to C. I assume that 0 is sent to 0 by f. And for simplicity, I also assume that I have isolated singularities. Okay? But mainly in the formulas I will give later, we may assume that we are in the general situation with general singularities. So the picture you have to have in mind is the following. You have the spatial fiber. In some small sphere. I choose eta for the radius. Okay. We know that this is a semi-algebraic set. This guy is an algebraic germ. Since we cut with a sphere, we are no longer algebraic, we are semi-algebraic. We have inequalities. This is why I introduce in lecture 1 semi-algebraic sets, because what I want to study here is a Milnor fiber seen as a semi-algebraic set. And you have nearby fibers in blue. Around, some sense, around the spatial fiber. Also seen in in the small ball, center on the origin with a small radius enough. So we know by the local conic structure of semi-algebraic sets that the white fiber is contractible. There is no topology. But here, we don't know. What we know about the nearby fibers is that they are smooth. Why it is so? Because the set of singular values of F is a semi-algebraic set. The set of singular values is a semi-algebraic set. And okay, it turns out that in the complex case, this semi-algebraic set has dimension 0. If we are in the real case, it is obvious by third theorem. But it is also the case in C. So it means that since a zero-dimensional semi-algebraic set is a finite union of points, that 0 is a singular value, and we don't have singular values in a small disk around 0. Other singular values are away from a small disk around 0. So if I pick here some epsilon in this disk, the preimage of epsilon has to be a smooth manifold. So the blue manifold is a smooth manifold, but of course, the topology may be very complicated. So my picture was too naive. You may imagine a certain number of holes in the blue manifolds. And since when epsilon goes through 0, the blue set goes to the white one, it means that here we have cycles that vanish when epsilon goes to 0. Since the topology of the white set is a trivial topology, the topology of a point, it means that when epsilon goes to 0, those cycles here in blue always exist, but at the limit they disappear. In the white object, no cycles. In blue object, the same number of cycles because we have a smooth bundle. Here we have a smooth bundle, say by Erasman theorem, for instance. So if you are away from singularities in the compact situation in the closed ball, you have a smooth fibration. So the blue topology is the same, whatever is epsilon. And at the limit, when you arrive in the white object, the blue cycles has disappeared. And by a theorem by Milnor, but I guess that Michel explained already this. Okay, so by the theorem of Milnor, the number of cycles is denoted by mu. Cycles meaning that, in fact, we have a mu sphere of a real dimension n minus 1. Okay? And the topology of the nearby fibers is a bouquet. When I say the topology, the homology, in fact, is a bouquet of mu copies of S minus 1. It means that the Euler characteristic, for instance, of the nearby fibers is given by, so you imagine you have here a bouquet of mu sphere. Okay. So you have mu multiplied by the Euler characteristic of this sphere, which is 1 plus minus 1 power n. But I have to to subtract mu minus 1 points. Okay? So it gives 1 plus mu. So we know how to compute the Euler characteristic of the nearby fibers. But we would like more. We would like more interesting invariants in this situation. So if you remember the first lecture, we have a convenient deformation now of the singular object we would like to study. Even if the topology is stupid, we still would like to study the white object. We have deformation. The blue objects are in family give a deformation of the white object. So we have a convenient family. We would like to apply some invariants and product formal series built on this invariant and see if we have some rational property for this formal series. But in fact, this deformation family is not enough. It's too the situation is too involved in this picture. So what we do is taking a resolution of singularity. So instead of looking at this picture, we take a resolution of singularity. We can do that. We don't know explicitly, well, we know explicitly how to do that, but it's a very, very complicated process. But anyway, it does exist. So we take a resolution of singularity of the germ. And with exactly the same notation as Michel, we assume that that sigma is proper and birational isomorphism away from the singular set. So away from the white set, we have an algebraic isomorphism. Okay. So we understand everything away from the singular fiber. We also assume that F composed with sigma is normal crossing. And we assume that the Jacobian of sigma is also normal crossing for technical reason. We denote by I don't know if you took the same notation, Michel, but we denote by capital G the set, a set of, and this is for irreducible component of the exceptional divisor, which is the preimage of the singular fiber. So you have to imagine that the white object yes, okay. The white object is in the resolution above union of irreducible varieties. Okay, so this is a picture, for instance. So you have, say, E1. E1, E2, E3. Okay. We also assume that the preimage of the origin by sigma is union of the components of the divisor Ej. And we have a natural stratification here, given by section. If I intersect two components, say E1 and E2, here I define the intersection as E12. Okay? But since I want a stratification, I would like to subtract here the point given by others components. So I denote by, for set of indices in J, I denote by EI, intersection of highest dimensional components in the divisor, in the exceptional divisor, and I subtract the union of. Okay. Same notation as Michel. Let's take some example. I take, sorry for the triviality of this example, I take f xy. Okay. So here, if I want to find a resolution of singularities, I only blow this point once. So if I blow once, here I have the projective space, and I now separate. I have to choose some color and fix the colors. Okay, I stay with white. So here I have one component, and so this line is a pre-image by sigma of this one, and this one of this one. Okay. Here we are, and now the nearby fibers are given by hyperbolas. In the real situation, the picture depends on the sign of epsilon, of course. Here I have the special fiber. And now I lift the blue fibers in the resolution. So if I do that in a smart way, maybe it's better to draw the hyperbola in this quarter plane. If I do this in a smart way, I see that above this branch, I have something like this, and above this one, I have something like this. Fortunately, my bright co-author Goulven is here today, so if some mistake, please correct me. What we have here, we have in red and white, we have the pre-image of the special fiber, and in blue, I have the pre-image of the nearby fiber. So what I pretend is that it's much more convenient to understand this than this. Why? Because everything is normal crossing. It means that I have some. I am in this situation along some components. Okay. along some stratum given the set of indices capital I, the composition F, the composition of F and sigma is given by powers with coordinates of EI multiplied by some unity, which is by definition not zero. Not zero over the open stratum. Okay. So it's much more interesting to have this expression of f than working with a polynomial f. In particular, I have a discrete set of powers here. I have numerical data that I can use to compute efficiently the topology of the nearby fiber. Let's try to compute the Euler characteristic of the Milnor fiber in this picture. Okay? Let's try to do that. I take a small neighborhood of the origin, and I am interested in the topology of this guy. So I lift the yellow disk. If I lift the yellow disk, I get a neighborhood of the red component, since the yellow disk is a neighborhood of the red point. Okay. So I have something like this. I have a kind of tube around the red projective space. Okay. And the lifting of the Milnor fiber may be seen here. So what you observe is that I have a covering of the strata, of some red and white strata by the blue lifting. Since I have this expression locally at EI, so if I get the pre-image of epsilon in the resolution, I know that I have a certain number of leaves above the strata. The number being given by this power. Okay. So since those strata project homeomorphically, since those leaves, the blue leaves in the resolution project homeomorphically on the open strata, I can compute the topology here using additivity. So what I see is that the white fiber is contractible. It means that here, what appear here give no contribution to the topology. I can contract to this point. Okay. So what I see in blue here is in fact above this intersection point. This intersection point, if this guy is E1, this guy is E2, and the red one is E3, the point is E1 free. And this point is E2 free. With the notation I introduced. So above this point, F is given by powers, and Now, above this open stratum, here I see a piece, a certain number of pieces, 2 pieces in my picture, given by the expression of f along this open red component, red stratum. So computing the topology by additivity, we see that we have here the Euler characteristic of this part, the Euler characteristic of this part, and I have to multiply by the powers here. But in fact, in the complex case, this part, given by, say, okay, in the resolution, this part is a product of S1. It's a tori. So above a strata of a small dimension, taking apart strata of the highest dimension, hypersurface strata, taking those apart, above all the other strata, you see that you have tori. Okay? So the topology here, the Euler characteristic here, is 0. So there is no contribution in the Euler characteristic of those parts. So above a small dimensional strata, you have no Euler characteristic. So the Euler characteristic is completely given by the blue parts above the red strata with maximal dimension. So we get that the Euler characteristic of nearby fibers is given by the sum of indices such that EI is in the red part, which is a preimage of 0. I have multiplicity here, and now the Euler characteristic of EI. Okay, simply by additivity and remarking that above small dimensional strata, we have tori with vanishing Euler characteristic. This formula, in fact, is a part of a much more general formula called a Campo formula. Maybe, Michel, you mentioned this. The Campo formula, in fact, compute the Lefschetz number of iterates of the monodromy of the singularity. But at the 0 level, this formula gives the Euler characteristic. Okay. So now, I hope that I convince you that looking a resolution of singularity is much more convenient, even if there is some complexity in computation, but it is much more convenient. And now I switch to the real case. The same situation, a polynomial ascending 0 to 0 with an isolated singularity at the origin. Same notation. I take a resolution, I take the canonical stratification in the resolution, and I can perform the same computation to compute the Euler characteristic. But in a real case, there is something which is notable. The fact that we don't have a smooth bundle in the complement of the origin, because it's not the complement of the origin is not a connected set. Okay. So we have, in fact, 2 topological types for the Milnor fibers. We have Milnor fibers related to negative epsilon, and the Milnor fibers related to positive epsilon. Okay. So this is the first difference. And there is another one. If you want to compute the Euler characteristic, here, you don't have such a magic simplification given by tori. Here we really have to take into account strata in the canonical stratification of small dimension. We don't have a vanishing Euler characteristic. So the formula is the same, but is the same. I mean, we have the same kind of formula by additivity, but involving now all dimension of strata in the real case. So the formula is much more complicated. You see that in the complex case, C star is the same as S1, and the Euler characteristic is 0. This is what I have used. But in the real case, I don't have C star, I have R star. And the Euler characteristic of R star is not 0. The Euler characteristic of R star is -2. So instead of having a 0 in those pieces, for the Euler characteristic, I have -2, -2, -2. Okay, again, the same notation as Michel. L is a space of arcs. Space of arcs in of formal arcs in on R D. So arcs, formal arcs with D components. And I take a reduction of this space, denoted by Ln. The space of polynomials with degree at most n, polynomial arcs with degree at most n. Okay. And now, definition. So here comes my zeta function, my zeta series. I consider a set of five symbols. The first one is called naive. The second one is -1, 1, bigger, less, strictly bigger, strictly less. And for such symbol denoted epsilon in this set of symbols, I define a zeta function depending on epsilon with a variable t given in the following way. So I sum over all integers. Je n'y vois strictement rien. Je pense qu'il est temps que je change de lunette. So I define a point carré formal series with variable t. I localize by the class of the line. So there is some inverse of the line here for technical reasons. And if you remember the first lecture, everything is contained here. What kind of invariance here I consider in the deformation. So I have to explain the coefficients. What is X naive? This is a set of polynomial arcs with degree at most n, such that by composition with F, I get a leading coefficient which is not 0. This is the first possibility when epsilon is naive. In case epsilon is -1, the same definition, but A is -1, okay, and so on. X1, A is 1, X bigger than, A is bigger than 0, and X smaller than, A is smaller than 0. Okay. So here are the deformations I consider. The deformations are given in a set of arcs. As you see here, in the three first situations, I have quasi-projective algebraic sets. The set of polynomials satisfying those equalities or inequations is a quasi-projective algebraic set. But in the two last situations, I really get a semi-algebraic set. A set of polynomial arcs with degree at most n, such that the leading term in the composition is bigger than 0 or less than 0, is a semi-algebraic set. Okay? And here I take the class of the set in, I could take the class as a formal invariant, formal additive and multiplicative invariant in this Grothendieck ring. But it is maybe much more convenient to take the class in the realization of this ring, namely in the tensor product of the Grothendieck ring of value by the ring of powers, inverse powers of 2. And if I want to be more accurate, in fact, here I have a formal series in T, but with coefficients in this realization. Localized by localized by the class of the line. So I have families of coefficients that have to be considered as deformation in the space of arcs, deformation to the singular set I want to study. I have a universal additive and multiplicative invariant here defining the coefficient. And I plug everything in a Poincaré formal series. And now with Michel, did you introduce the notation E0 tilde for the gluing of the boundary of tubes around? You didn't. Okay. Let me give you the theorem. So again, you will find this theorem is in our paper. Whatever epsilon is, this zeta function is a rational function given by the following expression. I take the sum over all subset of indices such that there exists a small I, such that EI is included in. So in short, I consider strata, all strata in the stratification of the preimage of 0 by sigma, the red strata. So those strata are the red strata. So I take the sum. I do not consider the white strata in this sum for the same reason as before, because the white singular fiber is contractible, so I can contract here on a smaller red strata in order to forget the topology above the white pieces. Okay, I only consider red pieces. Okay, this is the idea, and the formula is very comparable to the one given by Michel. Here I have a class of something that appear. And I have this product. Nu I is something given by the fact that the Jacobian of sigma is normal crossing. Nu I are powers appearing in this normal crossing expression. Ni are given by the expression of f composed with sigma along EI. So what is this guy? What is this guy? This guy is obtained as an algebraic set, as a gluing along EI of the following set. So I add a new variable t here, new variable t. So here I am in some chart. T is a variable in R, and I consider T M being the GCD of the Ni, multiplied by the unit appearing in the normal crossing expression of f composed with sigma along EI, and here I have some normal I have some symbol which is depending on epsilon, which is equal -1 in case epsilon is -1, which is equal 1 in case epsilon is 1, which is bigger than 0 in case epsilon is maybe I should write is and so on. Okay, so I have a kind of cover, and here I have a GCD of the. I have a kind of cover with a certain number of leaves of the strata. So for each stratum, I have this set around the red stratum, and I glue along all stratum. Okay, I don't want to go into details. So what is remarkable here is that, in the same way as in the complex case, we have a rational expression for the Poincaré series. And the proof is mostly the same as the proof Michel gave, mostly the same. You just have to take care at some point that we are not in C, we are in R. So those set appears quite naturally in the proof. Okay, those set appear, and that's it. And the computation, of course, is done in a resolution of singularity, same proof. But now, okay, we have something which is maybe interesting. We have a rational expression for formal Poincaré series, but we don't know what we did, in fact. In fact, we mimic the game we play in the complex case, considering this kind of Poincaré series, but we don't really know what we did from the topological point of view. Do we have something in end here? Do we have something in end that helps in the computation of the topology of the Milnor fiber? This is not completely clear at this level. What is clear at this level is that this expression seems to depend on the choice of the resolution. Because the nu I, ni, and those guys depends on the choice of the resolution. Depends on the picture I draw here. Okay? If I take another resolution, I have another expression. But what is for sure is that this guy does not depend on the choice of the resolution. So we have a first corollary here. This expression does not depend, in fact, of the choice of the resolution. If you take another expression by the game of identification in our ring, identification of those classes, you have to observe that we have the same expression. First remark. And now we continue to mimic what Michel did in the complex case, since Michel was a model for us when we were written this article. We have a picture of Michel in our bedroom, and yes, and yeah, and we play a lot in front of this picture. Sorry? With a cusp on his face. Yeah. Okay. So we play the same game. Oh, by the way, an exercise which is not difficult. The computation of the zeta function of our favorite example, the hyperbola, using this formula, of course, using this formula. Exercise. Take a resolution. Here you have a resolution. Take a chart of the blowing up and compute the composition of F and sigma. You have something like x, y square. Okay, so you have the ni. Compute the Jacobian. That takes the Jacobian matrix of x, y square. Compute the determinant. So you have a nu I. And now compute the class of those guys. So you form the GCD. You see what you get. Above a point here, the unit is 1. Above a one-dimensional stratum, you have x or y square as unit, depending along which stratum you look at. So you can compute this this guy as a semi-algebraic set, and it's not difficult to compute the class. You can express this class as a polynomial in L in the class of the line. The example is easy enough, and you get this this expression. Okay, so now I make this formula even more simple. The motivique réelle Milnor fiber, denoted by SF, but it depends on the choice of the symbol epsilon. We have 5 possible choices here. By definition, it is minus the limit. Of course, the limit here has no meaning, but nevertheless, it is the limit. The limit as t goes to infinity of this formal sum. Okay? So take t goes to infinity. What we have here is the same powers, but here you have minus. So some minus 1 power the length of the set of indices are going to appear. So we have here the sum over I such that there exists I in I with ei in the pre-image by sigma of 0. We have minus 1, length minus 1. No, this is yes. And here you have again this guy, the class of this guy. Okay. You have L minus 1 to this power, appearing here. This guy stays. And here we have minus 1 to the length of this set of indices. So we have, in some sense, a realization of this rational expression, which is now in our ring. So now we have something which is in and in the complex case, we have the same kind of expression, and we know that by taking realization of this expression by the Euler characteristic, it means that every time I see a class of algebraic variety here, I replace this class by its Euler characteristic. So here I have the class of R. I replace R by minus 1, which is the Euler characteristic of R. Here I have some fancy guy. I take the Euler characteristic of this guy. We know that in the complex case, if we take the Euler characteristic of the motivique complex Milnor fiber, we obtain, comparing with the computation we made previously here, which is the Acampo formula, comparing with the Acampo formula, we see that we get the same integer as in the Acampo formula. That is to say, we get the Euler characteristic of the Milnor fiber. So here, in the complex case, if I take the Euler characteristic here, comparing what I get with the Acampo formula, I know that I have the Euler characteristic of the Milnor fiber. In the complex case, here I don't have R, I have C. The line is C. And the Euler characteristic of C is 1. The Euler characteristic of R is -1. But the Euler characteristic of C is 1. So if I replace here everything by its Euler characteristic in the complex case, we have here a lot of factors that have to cancel. Each time this power is not 0, here I have cancellation by taking the Euler characteristic. It corresponds to the cancellation of those parts. It corresponds to tori. So in the complex case, I only have to consider a set of indices of length 1. If I don't want here to have a positive power, I have to have a 0 power. So I have that. You have to consider a set of indices with a length 1. It means that in the complex case, the realization of this formula by chi gives a sum over all maximal dimensional strata in the preimage of 0 by sigma. This is the computation we made. Okay. But in the real case, I have to replace L by -1. So I don't have cancellation in this formula. I have -2 to any possible powers here. I have a very, very long and complex, complicated sum in the complex case. But it turns out that we still compute the Euler characteristic. So the realization of the motivique réelle Milnor fiber is in fact the Euler characteristic of the set of points satisfying system given by epsilon. So let me introduce some notation. I give you the light version of okay, so this is in case I give you only two statements. So in case epsilon is -1, 1, we have this with f epsilon with f epsilon, okay, z f epsilon is nearby fiber, so in case epsilon is -1 or 1, but f epsilon is the preimage of some small open interval. So instead of taking the preimage of the hyperbola, I take the image of all hyperbolas now. Okay, so this is in case epsilon is. So I get another kind of type of Milnor fiber. You see, in case epsilon is this sign, I take, okay, here in fact I have C is assumed, sorry for the complexity, C is assumed to be a positive number, and in case epsilon is, okay, this is very complicated to state. I have to introduce C epsilon, which is a negative number in case I am in this situation, and which is a positive number in case I am in this situation. So it's better to understand this on a picture. This guy, when epsilon is this sign, is a pre-image of this semi-algebraic set. Pre-image of a semi-algebraic set by F. It is only, sorry, it is only. And in case epsilon is this sign, then I take here the complement. So I have a kind of a real semi-algebraic Milnor variation. And the bar here is the closure. The bar is just the closure. So it means that these 5 motivique real Milnor fibers compute the Euler, after realization by the Euler characteristic, it computes the Euler characteristic of the corresponding set of points satisfying those semi-algebraic formulas. So we really did something. We really compute the Euler characteristic of what we wanted to. And we also have, by the way, a relation with the open Milnor fiber, okay, for other reasons. So the idea is that we mimic the complex theory. We found a much more complicated motivique Milnor fiber with much more terms in the sum. It was not obvious from this expression that taking the realization by chi, we could compute some Euler characteristic of some pertinent object we have at the beginning. But in fact, yes. But in fact, yes. Yeah, so now to finish, some questions. We look this motivique Milnor fiber at the lowest possible level. We took the lowest realization, the lowest possible realization using chi, the most elementary additive and multiplicative invariant we have in N. Okay. Can we say something at highest level from this formula? On the other, in other words, let us consider the set of points let us consider this set as a set of points in RD, okay, given by a basic semi-algebraic formula. The most elementary basic algebraic formulas we can find for this is okay. So now the set of points of this basic semi-algebraic formula is this Milnor fiber. And is it true that in our ring, this formula is the same as any other basic semi-algebraic formula with the same set of points? Now, let's consider another basic semi-algebraic formulas with the same set of points. There are plenty possibilities. It's clear, several possibilities. Is it true that we have this? The answer is no. If I take realization by chi, the answer is yes. But at this level, in general, the answer is no. And even at the level of beta, even if I go down up to beta, we may have different realization through beta of different basic semi-algebraic sets. Okay, so here, okay, I'm not accurate here. You have to understand that this is the motivique Milnor fiber built on those formula. Yeah. This is not only formulas. So, here it's okay. At this very low level, everything is okay. But at this level, we don't know what we have did. If we change the formulas that gives the real Milnor fiber, we don't know what we do. Taking the Euler characteristic is the same as taking here as evaluating u at -1. And if we have the chance that at the level of classes we have a polynomial in L, taking the Euler characteristic is the same as replacing L by -1. It means that in case we have a polynomial expression in L, mod L plus 1, taking a reduction mod L plus 1 gives the same the same classes. So the question that François Lozer asked us is the following: if we consider mod L plus 1 relation for basic semi-algebraic formula with the same set of points, with the same set of points being a Milnor fiber, do we have equality? The answer is trivially yes, in case we have a polynomial expression in L. But since we don't know how to compute in this ring, we don't know, of course, how to answer this question. So I stop here.
The main point should be if you take the empty set. If you take the empty set.
Empty set, yeah.
Look at all the formula which define this.
It's because in the real case,
so if we take the empty set, do we have at the same time, when we look at the motif, something which is a multiple of A plus 1? Because the difference between A and B is an empty set.
Yes. Yes, it's the same. It's always this problem of finding a kernel of some morphism from a very formal thing to some convenient thing. How to compute the kernel.
First question would be to add a finite number of variables or parameters or an infinite number of them. And which infinity for the characterization? I don't know.
Probably. Yeah, of course, yes. Yes, because this ring is really a monster. Yeah. It's not a domain. I mean, it's probably yes. We have moduli in algebraic geometry. So okay, in stupid families we may have moduli. So we have to maybe to make some computation for elliptic curves or something like this. It's for sure very, very complicated. Okay.